Okay, guys, welcome back to the guided tour of Lux. Today, not today, in this video, um, we're gonna be exploring a subject that is gonna take a little bit more time. I want to go back to videos 20 minutes or less if I can, but this one is probably gonna take a little bit longer because there's a lot to talk about. And this because this video is about macros. And for those of you who are, you know what, screw it. I don't care if you're a Lisp programmer. I don't care if you're not. I'm gonna blow your mind nonetheless. Because even for you guys who might have experience with other Lisps, like Clojure, Common Lisp, or whatever, Lux macros offer a lot of things that those Lisps don't offer. And it's gonna be really cool. And you're gonna see how Lux macros are some really interesting tools. And we're going to be exploring those things over a series of videos because right now this is going to be like the basics of macros. And there are some more advanced stuff for future videos, especially for the next video, which is going to be for tomorrow. But let's go with the basics, right? So for those of you who might not be familiar with the concept of macros, even though we have used quite a few, and I have mentioned, some of the macros that we have seen, like the piping macro here, or this do macro here for working with monads, and we have actually used quite a lot of macros. Program is a macro, case is a macro, this arrow here is a macro, all is a macro, def is a macro, import is a macro. We have been using macros, if down here, if is a macro. We have been using a lot of macros so far. A lot of macros. And we really haven't talked too much about it. So I guess, now it's time to explain what are macros for those of you who might not be familiar with the concept. So macros are very simple, but they're not a feature that you tend to see in the vast majority of programming languages. Now, some of you who might be familiar with the C programming language, you might have heard about the concept of macros there, and in a way they are similar, but in a way they are different. They're kind of the same thing as far as intent goes. They both try to do the same thing, but they're both implemented. Lisp macros and C macros are implemented in different ways. They work at different levels of abstraction, and so you don't really get the same results. In general, Lisp macros are more powerful. But now I'm going to explain to you what Lisp macros are, so hopefully you will understand why they are so powerful. So, a macro is simply a function that is run at compile time instead of at runtime. So in most programs, when you use functions, they are run at runtime, right? So this factorial function here, I'm not using it anymore, but I'm using the list iterate function. This list iterate function here and this text types function here, they're only going to be invoked when I run the program and nowhere else. Well, imagine if you have a function that is run when the program is being compiled instead of when the program is being run. Now you might think, but who runs it? After all, when we run functions, when we run the programs, and those programs are run by the JVM, the virtual machine, or by the computer. Who runs the thing at compile time, since it's not technically running? Who does that? Well, the Lux compiler sees functions that are classified as macros and runs them at compile time. Now, another question that you might have is, okay, now I know who runs the macros, but what do they work on? After all, when you run a function, you're giving it numbers, you're giving it text, you're giving it users, you're giving it database connections, you're giving it things to run, because it's not going to run in isolation, it's not going to run without parameters, otherwise it will be a very boring function. So what do macros receive, and also what do they return? What are macros supposed to get as inputs, and what are macros supposed to produce as an output? And the answer is very simple. But we're going to have to talk about a little bit about monads, because macros in Lux are monadic. They are monads. and that has an impact on how they work. So basically, there is, in general, macros are a form of metaprogramming. For those of you who might not be familiar with the concept, metaprogramming is when you make programs that program other programs. It might sound weird. It's kind of like Inception. But it kind of goes like this. When you do normal programming, you make a program that works with numbers and text and booleans and produces a result for an end user. Maybe some statistics, maybe some calculation, maybe some simulation, whatever. When you make a metaprogram creates other programs on behalf of the user. So, for instance, the metaprograms are great for when you want to generate code automatically without having to do it manually, because it will be very tedious or error prone. So, for instance, let's say you have some schema definition for your database, and you would like to have types and functions for working with entities from that database in an intuitive way within Loox. But you don't want to write that stuff yourself, because you will have to write about a lot of stuff, a lot of query code, a lot of data types that match the schemas, a lot of conversion functions, a lot of stuff that you might not want to do. Well, what if you could write a program that if you give it the schema for the database, it's going to make for you all the code you need for working with the database as if you were working with normal Loox code. Well, that would be amazing. And that will save you so much time. And most importantly, you wouldn't just save time on writing the code, you will save time on debugging. Because since the program is making that code, you don't have to worry about human error. And yeah, you might say, but what if someone makes a mistake when writing the program that makes the code? Well, that can happen. But those mistakes are easier to fix than having to fix the same mistake multiple times in every place in which you did the manual code writing. So it's kind of like, when you have some code that runs in a loop and it has a bug, you solve the bug once and it's fixed for all the iterations of the loop. It's kind of like that way with metaprograms. You fix the bug in the metaprogram, and then all of the code that is ever generated will come out perfect. Well, macros are the primordial tool for making metaprograms in Loox programming language, and not just in Loox, in the Lisp family of programming languages in general. They're not the only existing tool for metaprogramming. There is also a tool called Reflection, or an approach called Reflection. You might have heard about it. For instance, the Java programming language offers tools for reflection. But, even though you can do reflection in Loox, reflection is mostly good for getting information about types and stuff like that, but not so much for generating code. For generating code, you will want something more like macros. So, as I mentioned previously, a macro is just a function. So, we have seen the types of some functions here. We have seen the type of this here, the type of this factorial function, and we have seen the type of this power function, and even the type of this list iterate function. So what is the type of a macro? Well, the type of macro is defined like this. And it's actually defined pretty much the same way in the standard library. And yes, there is a macro type in the standard library. So there is a function that if you give me a list of AST, I'm going to give you a looks of list of AST. Now this looks very weird. So, what is this? What is an AST? What is a looks? I mean, is it looks supposed to be a programming language? Well, AST is an acronym that stands for Abstract Syntax Tree. For those of you who are not familiar, an abstract syntax tree is a way to model the syntax of a programming language as a data structure. So it has multiple cases. So for instance, I can have a node that represents text, I can have a node that represents an int, or a real, or a boolean, and no connection for now. I have a node that represents, basic data types. I have a node that represents a tuple. There's a tuple node that can contain other nodes. I have a node that represents records or forms, which are, forms are just, structures bounded by parentheses. They will all be nodes within my abstract syntax tree type. There's actually a type for that, which is called AST. This is a type that represents the syntax of looks, and yes, it is part of the standard library. And finally, what is this looks type here? Looks kind of weird, and as we can see, it is parameterized. Well, here's the thing: macros in looks have access to the state of the looks compiler. So all the information that the looks compiler manages, every single bit, no exception, can be accessed by a macro at compile time. And that is very useful because macros can then use that information to look up information about definitions, about types. They can figure out things about, they can ask, which modules have been imported so far, which module owns me, which module am I being compiled, what are my imports. I can ask all the information that Looks compiler manages within a macro, and I can use that information to generate really powerful code. So the Looks type is a type that basically says, it is defined like this. The type looks of A has a type parameter, and it's a function that if you give me an instance of the compiler data structure, I'm gonna give you back another instance of the compiler and an instance of an A type. Okay? So basically it works like this. If you give me a compiler, I may or may not modify the state of the compiler, which is why I can return another instance, which will be a possibly updated instance. Now most macros don't modify the state of the compiler, they just look up information and that's it. But the option is open for people who might want to modify the state of the compiler for whatever reason, so you can change the state of the compiler if you want. And you can return some piece of data, and it could be anything. For instance, if I'm looking information about a definition, if I'm looking some type information, I might want to have a computation that, given the state of the compiler, gives me back a type that I got from somewhere within the state of the compiler. And you can have that. So the looks type is for computations or functions that can access the state of the compiler, which are basically stuff that uses some kind of reflection to get the state of the compiler and do something about it. It could be a macro, it could be something else. Then there are a lot of tools that work with the compiler that are not macros, but that are used by macros for getting information, asking questions, that kind of stuff. So a macro is simply a function that if you give me a list of ASTs, which will be the inputs of the macro, then I'm going to access the state of the compiler, and I'm going to give you back an output list of syntax tokens. So a macro is basically a transformation of syntax. I take syntax and I generate syntax in arbitrary amounts. So how do you make macros? And how they kind of work, Well, usually we have a def form, a def macro for making normal definitions, and we have a def type macro for making types. We also have a def macro, and yes, this is also a macro. I know it sounds crazy, but yes, you define macros using a macro. So there is a def macro, give it a name. You will be taking in some tokens, which will be the list of ASTs that you're going to be receiving. And then you do something. You do whatever. And of course, you can export macros and do whatever you want. So let's actually define a macro and see how it looks like. How does it work? Well, we're going to define a very simple macro first. It's like the simplest macro you could possibly write. It pretty much does nothing, actually. So this macro is going to be called comment, and it's actually defined already in the standard library, but we can redefine it ourselves here. We're actually going to be we're going to omit it, so the imported definition we get from the standard library doesn't interfere with the one we've got here. So we have this def macro comments. And comment basically does, you give it an arbitrary amount of code, and it just swallows it all up and makes it disappear. So it is great, for instance, if you're trying to comment out code, but you don't want to lose, the coloring and the structure and the formatting by using normal loose comments. Instead, you just want to make the code disappear, but keep it around. Maybe because you don't want the code to have any effect on your program, but maybe it's great for like a way of saying, hey, I'm commenting this right now, but later on, we need to make a bug fix or whatever and bring it back into the program. I don't know. Depends on what you want to use it for. So in this, since I'm just swallowing up the tokens, I'm not doing anything about it. That means I'm gonna receive an arbitrary amount of tokens, and I'm gonna return an empty list of tokens. So what we're gonna do is say, first of all, we should import some modules. We're going to import the meta module, which contains the monad definition for the looks type. Since macros are monadic, and in future episodes you will understand better how. But right now we're gonna be using the looks monad, do looks monad. We're not gonna be using any variables here or anything, and we're just going to wrap. You might remember the wrap function from the previous video on structures and functors and monads. I'm gonna wrap an empty list. So basically, I'm gonna say I am creating an empty list of ASTs. There's nothing, and I'm gonna wrap it in my shouldn't have erased the types. Where did I put those types? Oh, there you go. Oops, I shouldn't have done it like that. Doesn't matter. So I'm gonna wrap this list of ASTs inside my looks type. Now this might look very weird because I'm saying, hey, I am wrapping data inside a function, but I'm not defining a function. I'm just calling this function. I have to define a function because a looks is a function because of this definition over here. But I'm not defining any function. Well, wrap for looks monad is actually defined like so wrap actually generates a function for you. Remember that episode when we talked about functional programming? This is one of the crazy and beautiful things you can do with functional programming. You can generate functions on the fly. So this just generates a function that if you give me a compiler instance, I don't modify anything and I just give you the value that is wrapped. Simple as that. Now also, I said that the looks type is monadic, which might look weird from the previous episode because in the previous episode we talked about how maybe, which is a data structure, is a monad, and how lists, which are also data structures, are also monads. But how is a function also a monad? Well, in a way this function acts as a kind of wrapper, because you can say that the function that I'm generating in wrap is a wrapper for this type. Sure, it contains a lot of weird structure. It contains a tuple with an element, with kind of element added to the tuple. It's not just the raw data type. There's also some extra stuff, and there's a function outside. A function that leads you into this data structure. So it is a somewhat complicated wrapper, but you can have a lot of flexibility in the wrappers that you consider functors in functional programming. And even though not all functors can be monads, because you will also need a way of wrapping things, which you don't always have for all functors, and you also need a way of joining functors and fusing them together, which you also might not necessarily have on all functors. But in the particular case of looks, yes, the looks type actually has a monad implementation. So with this comment form, we can actually comment out, with this comment macro, we can actually comment out this whole program code. So let's see what happens when you try to compile this. Oh, I'm sorry. I should comment this out. Let's just comment this using our newly defined comment macro. So it compiled perfectly, great. But now what happens when we try to run it? Bam! There is no main method defined for our program. As you might know, JVM programs need to have a main method defined to be able to run. Well, that's what the program macro does. It generates that for you, but since we didn't define it, we have no main method. We cannot run our program. It's just a bunch of compiled down things. No program. Well, it is because this comment macro here just made everything disappear. It just swallowed up all the code that was given and gave back nothing. So this is actually a pretty trivial macro. Doesn't do a lot. So why do we want to do something more complicated? Why do we want to replicate not just the comment macro from the standard library, but also something like this piping macro? Well, let's actually replicate it. It's actually very simple, and it's gonna be a more complex example of macros. Not a very complex one. It's still very simple. But for more complex macros, we're gonna need more tooling, and maybe this video, presenting all of the crazy things you can do with macros and all the crazy tools you have available, might make it a little bit too long. So we're gonna exploring the world of macros, piece by piece, over several episodes. So for now, let's just make this definition of piping, so you can see a more complex macro. So again, I'm receiving this, and what I'm gonna do is this. So I'm gonna pattern match on this. I need to make sure that the arguments that I am getting are well formed. They have to be, for instance, you cannot invoke the piping macro empty. For instance, in this particular invocation of the piping macro, I cannot just call it with nothing, because then there will be absolutely nothing to pipe. So we need to be able to handle the error case. So if the tokens are empty, we're going to fail. So fail is a function that we got from the meta module. Okay? So fail basically says, hey, oh right, I'm so sorry. This definition of looks, I'm sorry, it is incomplete. It is incomplete. It's missing a piece of information. So the looks type is an instance of the looks type is a function that takes a compiler and then returns either some text, which will be an error message, or a tuple with an updated compiler and a return value. So looks type functions can fail, and we saw failure yesterday in terms of maybe, but maybe doesn't give you any information about the failure. It just tells you that there is data or there is not data. There was success or there was failure, but you don't know why the failure happened. Well, when you do want to know what the failure happened, using something like either text is great. You're saying that either you're giving a text element that will be an error message, or you're giving this thing here. And either is just a type with two parameters. They can be anything, but for the purposes of macros and that kind of stuff, I want them fixed on an error message and an updated compiler state and some data entity. So fail basically means I'm giving back the error message. I don't care about giving back any data or updating the compiler state. And by the way, you might notice that here in macros, even though macros is supposed to take the state of the compiler, we're only taking in one parameter, which is the list of tokens. Now in macros we could take the state of the compiler also. We could do both. But most of the time it's unnecessary because functions like wrap and fail generate for us functions that already take the state of the compiler. So we can omit this step. Sometimes, for some macros you might want to have direct access to the state of the compiler, depending on some things. But for most cases, you really don't need it. It's mostly not useful. It's mostly not useful. So, now we know what happens when the list is empty. But what happens when there's at least one element? Well, I show you that the piping macro pipes things kind of backwards. So it puts this args element into this one, and the composite of both it puts into this one. So the first argument is going to be the most nested one, because it's always at each step is going to be nesting on subsequent deeper levels. So what we're going to do that is that we're going to reverse our list of tokens in order to process them in that way. Wait. No, forget it. I'm thinking of another kind of macro processing. Forget it. We're going to process them normally. So you give me an initial element, which will be our args list here, and you give me, other components, other expressions on which to do the nesting. I'm gonna do the nesting. It's very simple. So what I'm gonna use a function that we haven't seen before. I'm gonna import the list module. Gonna open the list fold data structure. We saw it before on the previous episode, and one of the functions that we're gonna get from that is gonna be called fold L. And I'm gonna give it this initial expression, this initial AST, and these other expressions. And by the way, remember that const works kind of like, you get the head of the list and you get the tail of the list. So this is a single element, and this here is a list of elements. Init is a single element, expressions is a list of elements. So fold, it takes a function that works on two elements. Let's call it to nest and parent, or parent child and parent. Initially, the child will be init and the parent will be express, every individual expression within this variable, because I'm nesting init in the other one, so init is going to become the child of the expression. So I'm going to have a function that works on two individual AST nodes. You give it an initial AST node and a list of AST nodes. Now, of course, fold L can work with lists and elements of arbitrary types because it is universally quantified. But for the sake of working with these data structures, for the sake of working with ASTs, we're just going to be using this. So this is a function that, if you give me two ASTs, I'm going to produce a new one. So I'm going to be pattern matching on my ASTs. And I'm going to show you some of the I'm going to show you how an AST node looks like, or at least some of them. So I'm going to have a special case if it's a form. And what happens if it's a tuple? The S prefix stands for syntax. So form syntax, tuple syntax. They both have expressions, and they will have a piece of metadata called the cursor, which tells you, which file, in which line, in which column this piece of syntax appears. And then I have, something else. I don't care. What happens if it's neither a form nor a tuple? So if it's not a form or a tuple, I'm gonna be just wrap them in a kind of function call. If it's not a form, if it's a form already, then I want to wrap everything this way. Otherwise, if it's a tuple, I want to make this into a form, I want to make this into a tuple. This syntax looks very weird. What the hell is this thing with the back quote here and this tilde add sign and this tilde here? Well, we're gonna be exploring this in future videos, but consider this as some kind of templating syntax for generating code, which is very useful for macros. So suffice to say, I'm saying, if you give me a form like this one, then I'm gonna make another form, which is this one, and I'm going to splice all the elements already existing. In this case, it will be these two things. I'm gonna splice them in my new form, plus I'm gonna add a new element, which is a child, and I'm putting it right at the end, because remember, piping works at the end. And for tuples, we get the same behavior, except that instead of generating a form like here, we're generating a tuple like here, which is why up here we have parentheses, down here we have brackets. So this is how you're going to generate a single piece of AST, because what Fold does is that it starts with an initial value and the list that might be empty. If the list is empty, then the result is just the initial value, and if it is not empty, then this function is going to be applied to the combinations of those values on pieces of 2 until everything has been processed and you end up with a single value. In a way, you have folded the data structure into a singular value, and then that is the return value of the fold function. So this is going to generate a single AST. We're going to call it result, but since macros need to return lists of elements instead of single elements, we need to wrap everything in a list. So, like in our comment macro, do looks monad, and inside the list we put this result, and this is gonna be the transformation of our code. It does the same thing as the original piping macro, but here we defined it ourselves, and you can see how you take in a list of element tokens, you can perform arbitrary transformations on them, and then finally you wrap them in the looks type and you return a list of the new tokens. So let's compile this. And compile properly. And let's see how this works. So remember, we are, as in our previous programs, we are iterating the inputs and getting the counts. So macros are cool. It works perfectly, which means that our piping macro worked perfectly. It correctly transformed our code from this here, which is very comfortable to write, to the nested version, which is somewhat more uncomfortable. Now, there is still a lot of mystery. There's still a lot of mystery involved here in these macros. A lot of things that have yet to be explained. We have seen this fold function that still looks a little bit mysterious, maybe to some of you guys. We have seen some. We have talked about monads, but we still don't know everything about monads and how exactly they work. And we are constantly putting this empty bracket thing. It seems kind of useless. But in the next few episodes, we're not just going to be exploring macros, but we're also going to be using monads for real, not just for wrapping things and that's it. So we're going to be making good use of this bracket syntax here, and you are going to understand how monads work and why macros, or at least looks macros, need monads to work. So for now, this is just a nice primer on macros, how to write them, what are their types, more or less how they work. We're gonna be talking about them much more in future videos, and especially we're gonna be talking about some of the tools, the amazing tools that can make writing complex and powerful macros piece of cake. Because right now we're doing things in the more primitive way, in the most primitive way possible. This is not the way I write macros in the standard library. Okay? This is not the way I do it. Because it's too primitive, you gotta do pattern matching on the list of tokens, it's really annoying. The moment you try to do anything complex, it's just a mess. But this is not the way you're gonna do it, okay? So in future videos you're gonna learn how to write macros like a pro. Okay, so for now, let's leave it at this, let's leave it at that, and I'll see you tomorrow with more of this guided tour of Lux. See you then.